Okay, so we are talking about convection. Convection, as we know that it is heat transfer mode when a flowing fluid is in contact with the surface. So it takes away heat, or rather it gives away heat. So convection is heat transfer between flowing fluid and surface. Surface can be stationary, surface can be moving, doesn't matter.
Okay.
Heat transfer due to convection. Okay. The basic formula given for convection was by Newton, which is Q is equal to HA delta T. Right?
Okay. Yeah.
This is called as
transfer coefficient, right?
Coefficient of convection.
Oh, okay.
It is called as coefficient of convection, and the unit was watt per meter square, either degree Celsius or Kelvin.
Kelvin.
Because Q, unit of Q was watt, A was meter square, and delta T was Kelvin or degree Celsius. Okay. Convection coefficient. This chapter is all about finding the value of H.
Okay.
Because otherwise there is nothing else. Which actually is a part of convection, is mostly all about finding the value of H. In this chapter, we are going to study two types of convection.
Okay.
Firstly, it is forced convection, and second, it is natural convection. Okay. I think in previous lectures we did had a discussion over the what does forced and natural mean.
Yeah.
Forced means using some pump or a fan or blower in order to flow the fluid, in order to move the fluid. That is where the convection is forced. Whereas in natural convection, the fluid flows on its own.
Okay.
Okay. By density difference. It is density difference which causes the flow of fluid. Okay, that is we had a discussion on buoyancy force and then density difference. That was all about natural convection.
Yeah.
Okay. I hope you remember everything, whatever we discussed for like in 5 minutes. Is there anything you need to ask about?
No, I'm good so far.
Okay. In forced convection, rather in this chapter, when we will talk about forced convection, it will be in two types of geometry. One will be over the surface, over the plate, over the geometry. It can be anything, or the fin. And secondly, it will be inside the pipe.
Okay.
Inside the pipe or duct. Okay, so there is like two kind of arrangement wherein the fluid will be flowing, one over the surface and one inside the pipe.
Okay.
So in order to find the coefficient of convection H, we will be talking about many numbers, many dimensionless numbers. Okay, before we start with the numbers, there are some basics we need to know if we remember from our past, like from the second year or the first year of the engineering. So let's see what we remember. Let's learn what we don't know. Okay. The first and most important parameter is viscosity. Do you remember anything about viscosity?
Yes, the resistance for flow, right?
Yes, it is resistance of flow. And again, the law was given by Newton, which is called as Newton's law of viscosity.
Okay.
And the formula was tau is equal to mu du by dy. Do you know this formula?
Yeah.
Okay. Tau is shear stress.
Okay.
Okay. Tau is shear stress. Mu is
viscosity of the fluid.
Yes, it is called as dynamic viscosity. Viscosity of fluid. Okay. And the du stands for change in velocity. Dy stands for change in layer or the thickness. It is called as velocity gradient.
Okay.
It is velocity gradient. It is the way velocity is changing with the layer. So
Okay.
if you understand through an example, it would be like, consider a surface over which fluid is flowing, or you can say, let us assume a layer of fluid. Let us assume a very small layer of fluid which is flowing. Okay, we'll take another color. Let us assume some small thin layer of fluid flowing over the surface. There are some intermolecular forces called as cohesive forces and adhesive forces. The adhesive forces is basically a force which is between the fluid and the surface.
Okay.
It is the force by which the surface clings the fluid, or the fluid clings to the surface. It is the stickiness. Okay. And cohesive forces is the force between the intermolecular particles, like the force by which one particle attracts the another particle.
Okay.
Okay. These are two forces which kind of, you can say, affect the viscosity, the intensity of these two forces. So when a fluid is flowing, because of the adhesive force, it will try to cling on the surface. It will try to hold the surface, but at the same time, it is experiencing some external force because of which it is flowing. This leads to shear. This leads to shear of the adjacent layers. Like the upper layer shears from the bottom layer.
Okay.
These are exaggerated form of the layers. They are like really thin. But if you can understand that whenever there is a water or some viscous fluid on this plate or the surface, and when you tilt the surface, you can still see that some part of the fluid is stuck to the
material.
That is the lowermost layer.
Okay.
Right? So this is how we can represent that the upper layer proceeds, whereas the lower layer try to remain at its position, and that's how adjacent layers gets sheared from each other.
Okay.
Okay, I hope you understand the phenomena of shearing.
Yeah.
Okay, so these are the adjacent layers which are getting sheared, and so you can see if the difference, or you can see if the upper layer has got some velocity, the lower layer will have a velocity lesser than the upper layer.
Okay.
Okay, and the thickness which we can see is basically dy, and see, this is the second last most layer, and below this would be the lowermost layer. So the blue color, so in blue color we can say it's a complete stagnant fluid, whereas in black color we can say there are layers of fluid getting sheared. The lowermost would be having negligible velocity. The layer above it would have some velocity. The layer above this layer would have more velocity, and so they are getting sheared. The difference between the layer is nothing but dy, and difference between their velocities are nothing but du.
Okay.
Right? This would be at higher velocity. This would be at lower velocity. That is, the difference can be represented by du. Whereas when this is like y direction, so difference between their position from the surface would be y2 minus y1 represented by dy, and it is nothing but called as velocity gradient.
Okay.
So there are many types of fluid. The fluid which has direct relationship between velocity and thickness are called as Newtonian fluid. And when you kind of draw a vertical line and join all these layers with their respective velocities, there forms a curve. Okay, you can say this layer has got lesser velocity, upper layer has got more velocity, the above layer has got bit more velocity, and it goes on increasing in this manner. This curve has a nature of parabolic profile. So this is a parabolic curve.
Okay.
Okay, this forms a parabola, and this has a parabolic curve. Whenever a fluid is such that the shear stress is directly proportional to du by dy, such fluids are called as Newtonian fluid. there are many other fluids which are non-Newtonian or some real fluid. All these fluid would have some power to this value, like power to the power 2 to the power 3 to the power 4. So eventually the formula would look same, but with small modification depending upon types of fluid. This formula would be having these 3 parameters and some more parameters, like shear stress would be always there, mu will be always there, and du by dy will be also always there. Okay, for heat transfer purpose for our chapter, majority of the time the Newtonian fluids are only considered.
Okay.
So it is like very rare when you actually have to go through other fluids. Mostly in case of case studies or in case of experiments or some projects, people go for non-Newtonian fluids. But for syllabus sake, we always deal with Newtonian fluids, where shear stress is equal to mu du by dy. Okay. Okay. Viscosity is very important, because viscosity is something which will either be given or you'll have to calculate it every time in this chapter.
Okay.
Viscosity is a parameter which will affect the heat transfer coefficient. That's why it is very important.
Okay.
Okay. Viscosity, if you understand, then the viscosity of a fluid for liquids, it always drops when the temperature of the fluid increases.
Okay.
Viscosity drops when the temperature of fluid increases, because it kind of becomes thinner.
Okay.
It loses its intermolecular forces.
Yeah.
So, and mu for gases, on the contrary, increases with the increase in temperature.
Okay.
Because the randomness increases, the kinetic energy increases, so they kind of bang to the surface at a higher velocity. And because of that, with the increase in temperature, the viscosity of gases increases. So this was about viscosity.
Okay.
Okay. Then there are some other parameters like kinematic viscosity. Have you heard this parameter? Okay. It is denoted by nu. Okay. Like dynamic viscosity is denoted by mu. The kinematic viscosity is denoted by nu. And this simply ratio of mu upon density.
Okay.
It is simply ratio of dynamic viscosity to the density of the fluid. It is also referred as viscous diffusivity.
Oh, I've heard of that, I think.
The name itself explains what exactly it would be. Diffusivity. It kind of signifies how it takes in the external force to behave its physical parameter. Like the way it will take the force inside it, it will move accordingly.
Okay.
Like, it's like when we are studying some subject, the faster we absorb the content, the faster we move ahead.
Yeah.
Exactly with the fluid, when the faster they absorb the force, the faster they start flowing.
Okay.
So that's how this diffusivity explains. Higher the diffusion, faster the fluid would flow.
Okay.
Okay. So that is all about diffusion. Okay. In this chapter, apart from kinematic viscosity, we need to also know a parameter called as thermal diffusivity.
Okay.
Have you heard this parameter?
Yes, I think so.
Thermal diffusivity is denoted by alpha. Okay. Alpha is function of, I think, density, conductivity, mu Cp upon K. It is K upon mu Cp or mu Cp upon K? I just need to cross check.
I think it's K over.
I don't know. I don't have the formula right now. I'll just see. I think it is K upon mu Cp. Mu Cp. I'll just cross check once I go, once I remember or recall. But I think it is K upon mu Cp. K is called as thermal conductivity. Thermal K upon mu Cp, K upon rho Cp.
I think it's rho.
I think it's rho.
Yeah.
K upon rho Cp, right?
Yeah.
K upon rho C, thermal conductivity.
Yeah. Over density and specific heat.
Yes, perfect. Yes, specific heat, and this is density.
Yeah.
Thank you. Okay, see, these are two parameters which will affect the heat transfer rate. Like thermal, like if you understand what is viscous diffusivity, it is about how easily it is taking force inside it to flow. This would be like how easily a fluid is absorbing the heat or taking the heat inside in order to function the heat transfer phenomena.
Okay.
Like if a fluid has got a function of carrying heat from one place to another, if a fluid is like a truck, if a truck has the function to transport the material from one point to another, then diffusivity is like how easily the truck is getting loaded.
Okay.
So if it can easily load the material, then only it can transfer from one place to another.
Yeah.
Similar way, diffusivity reflects how easily the heat is getting into the fluid, which has the property of transferring the heat by convection.
Convection. Okay.
So these are two parameters. Okay.
Okay.
We just now understood what is dynamic viscosity, then we understood kinematic viscosity, and then thermal diffusivity.
Yeah.
Then we will go through some numbers now. We will go through some numbers like, have you heard the word number, Reynolds number?
Yeah, Reynolds number.
Okay. What is Reynolds number? No issues. Reynolds number is basically, you can say it is relationship between viscous force and inertia force. Okay. It is a relationship between inertia force and viscous force. So what does it signify? It signifies that viscosity is something which is like resistance to flow, and inertia is something that a body carries while moving. Any body which has got a motion, it has got inertia. So it is like a fluid is also moving. If a fluid is moving, then inertia force is something that is required to push the fluid.
Okay.
At the same time, that inertia force will depend on the resistance the fluid is offering to that.
Okay.
Like you are standing, and if somebody is pushing you, the harder you grab the floor, the more difficult it would get for the person pushing you.
Yes.
Right. So viscosity is like the way you are grabbing the floor or holding something, and inertia force is something which is like someone pushing you to move.
Okay.
Right. So this is how they are related, and it is formulated as rho v d by mu. Okay. So the formula is inertia force upon viscous force. It is equal to force of inertia upon viscous force. Now, what is inertia force? Inertia force is formulated from basic Newton's second law formula, mass into acceleration, and then it gets formulated to rho a v square. You remember the formula, mass into acceleration formula?
Yeah.
Okay. That is how it is modified from that formula to rho a v square. Mass can be written in the form of density and volume, right? And then acceleration can have a function of velocity and time. Then later on, it is simplified and written in the form of rho a v square. Like force is equal to mass into acceleration. Then mass is equal to density into volume, which is area into length. Acceleration is velocity upon time. Then this can be written as area into length upon time, can be written as velocity. And then this can be written as rho a v square. Okay. So basically, inertia force, which comes from Newton's second law, mass into acceleration, can be written as rho a v square. And then just now we studied about shear stress. From shear stress, this formula, shear stress can be written. Stress is force upon area. Right?
Yeah.
Any stress is force upon area. Like pressure is force upon area, stress is force upon area. Shear stress is force upon tangential area. And this can be written as F upon A equal to mu. Du is nothing but velocity. Dy is thickness. Okay. So in this case, this formula F can be written as mu A V by T. Mu A V by T. Mu A V by T. Okay, this formula can be simplified in this manner for this fluid flowing on the surface. Then if we take a ratio of rho A V by T, sorry, mu A V by T, mu A V by T, this formula, mu A V by T. In this case, AA would get cancelled out, PV would get cancelled out, and this T can be written as diameter for pipe, because over here T was thickness of the layer, and in a flowing fluid, if fluid is flowing inside a pipe, over there this formula would be this T would be replaced by diameter. So if you simplify this, it would look like this: rho V D by mu. See, rho V and D goes in the numerator by mu, right?
Yeah.
So if I just write it down in simpler manner, it would be like rho A V square upon mu A V by D, where AA gets cancelled out, VV gets cancelled out, and the formula becomes rho V D by mu.
Okay.
Reynolds number has a terminology called as density, velocity, diameter, and dynamic viscosity. Okay. This is something which is for pipe, but it is not just pipe where Reynolds number is calculated. This formula is generated or formulated for pipe when a fluid is flowing inside a pipe. But Reynolds number is not just calculated only for pipe. So in that case, this diameter is called as characteristic length, depending upon the application in which you are calculating the Reynolds number.
Okay. So the diameter only applies in pipes.
Diameter, the characteristic length, or also called as hydraulic diameter, is only for a pipe. Whereas when a fluid is flowing inside a square duct or over a plate or a surface, then in that case, D is changed by characteristic length, and the formula is accordingly generated. Like if it is a duct, in that case, diameter becomes 4A by P. Like if you generate this formula for a pipe, if you try to make a formula for a pipe, A is cross section area of pipe is pi by 4 D square, and perimeter of pipe is pi D. You can see that pi gets cancelled out, 4 gets cancelled out, D gets cancelled, and only D is left. Right. So for duct, if it is in circular shape, 4A by P remains D. But had it been some other cross section, like if it is square shaped duct or rectangular shaped duct or any polygon shaped duct, in that case, you need to use this formula where A is cross section and P is perimeter.
Okay.
Like I will just write one more formula for a square duct. For square duct, area of square is side square, and perimeter is sum of all the sides, that is 4S. So 4 gets cancelled out, this gets cancelled out, this remains only S. Square duct, right? D square. Had it been rectangle, suppose it has got side AB. Okay, let me say this was pipe of diameter D. This was square duct of side S. Square duct of side S, and if it is a rectangle of side A and B, it would look like 4, and the area of rectangle is AB. Perimeter would be twice A twice B, 2A plus 2B. 2 gets cancelled out, and the formula would look like 2ab upon a plus b. That's how you can calculate hydraulic diameter or characteristic length for a rectangular duct in order to calculate Reynolds number.
Okay.
Any question?
No.
So this was about Reynolds number. Let us understand significance of Reynolds number by types of.
So can I just check with you one thing? So the D changes according to what instrument I have, meaning if it's a pipe or if it's a square pipe or if it's a rectangular pipe.
Yes.
Okay, got it.
Okay. If we are talking about internal flow, like these are all internal flows.
Mhm.
If it is pipe or duct, it is called as internal flow. Then for internal flow, for pipe or duct, the Reynolds number, if it is less than 2000 or sometimes 2300, the flow is considered laminar.
Okay.
If RE is ranging from 2000 to 4000, then the flow is called as in transition zone.
Mhm.
Transition phase.
Okay.
Transition phase. And if RE is more than 4000, the flow is called as turbulent.
Okay.
Do you understand all the types of flows?
Yeah, I do.
Okay. Laminar, transition, and turbulent. Transition sometimes can be referred as laminar or sometimes can be referred as turbulent. It all depends application to application. So most of the time, none of the numericals plays between these range. Either you will have a numerical lesser than 2000 or more than 4000.
Okay.
Okay. So this is all about Reynolds number when a fluid is flowing inside a pipe or duct. Okay. You should know that in laminar zone, the velocity profile, do you understand the boundary layer concept?
Boundary layer?
Boundary layer concept. Do you know the boundary layer concept?
No, not really.
Okay, we'll see boundary layer concept, and there I'll explain you about these Reynolds numbers in according to the types of flow.
Okay.
Okay. See, these are numbers for a flowing fluid inside a pipe.
Okay.
But if the fluid flows over the surface,
Mhm.
this diameter is replaced by L. This diameter is replaced by L. Instead of D, there is L, which is called as characteristic length.
So it's the length of the pipe?
Yeah, it is not the pipe, the length of the surface over which the fluid is flowing.
So surface area.
It is the span over which the fluid is flowing. Not
Okay.
the surface area. It is a span. Like if it is a surface from which the fluid has started flowing, then the span over which the fluid flows is the characteristic length.
Okay.
Okay. So external flow. This was for internal flow. If we are talking about external flow, then in case of external flow, let us consider plate, a big plate. In that big plate, a fluid has just started to flow. When the fluid comes in contact with the surface, at the very beginning, the fluid starts experiencing resistance, retardation, and slowly it loses velocity and it retards. And when the flow propagates, it retards more. It loses its velocity at a higher rate, and you can see that a small layer starts building up. Above this layer, the velocity remains same as it was before striking.
Okay.
And below this layer, the velocity kind of drops and it becomes negligible towards the surface.
Okay.
Okay. So this layer increases, the thickness of this layer increases with the propagation of flow, and at a particular length, let us say at distance x, till distance x from the entrance, from the leading edge to a particular length, you will find the flow always laminar. The flow is always laminar at the beginning of flow. Like from this leading edge to a particular distance x, you will always see that the flow is laminar below this layer, this imaginary layer.
Okay.
The thickness of this layer is called as thickness of boundary layer.
Okay.
The thickness of this layer is called as thickness of boundary layer.
Mhm.
Sometimes you are also asked about what exactly is thickness of boundary layer. In that case, you can answer that it is distance from the surface. It is distance measured from the surface to the particular layer where the velocity is approximately equal to the free stream velocity. You can say this is free stream velocity, or equal to 99% of the free stream velocity.
Okay.
It is, you can say 0.99 times u infinity. So velocity is 0.99 times u infinity. At this point, u would be 0. At this point, u would be 0. U increases, and at a particular height, normal to the surface over which fluid is flowing, the velocity would be 99% of the free stream velocity. And that height is called as boundary layer thickness. The boundary layer thickness increases from the leading edge towards the flow. Then at a particular distance x, the laminar property of the fluid kind of gets disturbed.
Mhm.
What is laminar property? The laminar property is wherein not a single particle of a layer goes below the layer.
Below the boundary layer.
To maintain the layer, they always maintain their particular lane of flow.
Oh, okay.
They will always maintain their lane, and they will not descend. Like the layer below it will not change its lane, and the layer above will also not change its lane. That is laminar flow.
Okay.
When the thickness of the fluid keeps on growing, there comes a point, because of its own weight, the uppermost layer try to descend. It try to get inside the lower layer.
Yes.
And that is where disturbance cause. That is where the turbulence propagate. That is where turbulence of the fluid start. And that zone is called as transition zone.
Okay. So that is laminar plus turbulent.
There is laminar plus turbulent. So from here, the fluid will be like, here the layer would be laminar, but the layer above would be like, let us go and change the lane. And they would penetrate into the lower layer.
Okay.
This is called as mixed layer or transition layer. Okay.
Okay.
But the thickness of boundary layer still increases with the flow. And eventually, after some point, you can see that the thickness increases and the flow is completely, or the layer is completely turbulent. It is like completely turbulent. And that zone is turbulent zone. This zone is turbulent zone.
Okay.
Okay. This is turbulent zone. And the thickness always increases. It always increases with the length of the surface. Okay. Then there are some other properties also, like called as boundary layer separation, which is not part of heat transfer. It comes into a chapter where you have to understand concepts like aerodynamics or boundary layer separation, or mostly part of fluid dynamics.
Okay.
In that case, we have to study this boundary layer beyond this point. But in case of heat transfer, we always study before that point. Like we always assume that the boundary layer is always in contact with the fluid, in contact with the surface.
Okay.
Okay. So here, why are we studying this? To understand that in this case, the Reynolds number RE is not in the range of thousands. It is in the range of lakhs. So here RE is like less than 5 into 10 raised to 5. Sorry. Okay. Here it is like in the range 3 into 10 raised to 5. And a point where the flow is completely turbulent, the RE is more than 5 into 10 raised to 5.
Okay.
Okay, but it is very difficult to predict this zone where it starts. So the threshold value is always considered as 5 lakh, 5 into 10 raised to 5. Like many times you will see that till 5 into 10 raised to 5, the flow is considered to be laminar.
So they do not consider the transition at all.
because it is not that easy to predict. It is not that easy to understand because of the
Just assume anything below that is laminar, anything
Yes.
above that is turbulent. Okay.
Yes. And we don't have to be confused about it, because not just about the value of 5 into 10 to 5. It is
Mhm.
like they still give you range beyond that. Like not just the value of 5 into 10 to 5, they give you to find, they ask you to find the values for the range of RE 5 into 10 to 5 to 5 into 10 to 10, 5 into 10 to 8. Like they always give you some range. So it is not something that which will bother us or confuse us.
Okay.
They will always give you some clarity about the range of the RE in order to find the unknowns.
Okay.
Okay. So
Can I just ask something? So this is for external flow, right? Does this also apply to the internal flow?
yes, it is applied.
Okay.
It is applied. Like this is about external flow. Similar way in pipes. If I draw a pipe, when the fluid enters the pipe, it has some initial velocity infinity.
Mhm.
When it comes in contact with the pipe, the fluids nearer to the surface will retard. It will retard.
Mhm.
And the layer would be like the centermost will have max velocity, and some fluid adjacent to it will also have similar velocity or same velocity, but the fluids near the pipe will have lesser velocity.
Okay.
Okay, so to understand it, we can say, excluding the fluid near the surface, all the other fluid will have velocity equal to the entrance velocity. And as the fluid will propagate, this phenomena will keep on increasing. Like this curve will try to bend more. You will see that this length over which, or this span over which the velocity was same, will reduce now. You will see that this curve will bend more because it will eventually retard the adjacent layers.
Mhm.
And with more or further propagation, this will shrink down and the layer would get more curvy. And there will come a point where only the centermost layer will have max velocity, and all the adjacent layers will have their velocity reduced, and ultimately it will be least near the surface of the pipe. Whenever, if the fluid is Newtonian, this curve will be in parabolic nature. Okay. Over here also, in the laminar zone or also in the turbulent zone, when you will try to draw a velocity profile, you will see that the velocity is negligible at the bottom, and the velocity will increase toward the surface, and it will have a parabolic nature over here also. So this is how the velocity profile would look over the pipe, and it will go straight beyond this, because here the velocity is equal to free stream. Beyond this, every particle will have free stream velocity. In this case, this is again parabolic. And from the entrance to the span over which this parabolic curve is completely generated is called as entrance length. And this flow, beyond this, you will always find the nature never changes. The flow will always be parabolic. Until unless the you can say laminar property is disturbed.
Okay.
If the flow is laminar, this parabolic profile will never be affected.
Okay.
If the flow is laminar, this parabolic profile will never be affected, and such flows are called as fully developed flow. Fully developed flow. Okay. These are not fully developed. So always there will be some span of the pipe which will not be considered as part of the heat transfer. The heat transfer properties are always calculated beyond this fully developed region.
Okay.
Okay, so this was about the boundary layer and the fully developed flow in the pipe. I hope
Okay.
you understood.
Yeah.
Okay, in this case, the RE would be less than 2000. RE would be less than 2000.
After fully developed?
Yes, after fully developed. And if the zone changes from parabolic, like if the zone changes from laminar to some other type of flow, like in this case, you will always find a laminar flow followed by transition and turbulent. But for the cases where you are studying pipes, either it will be laminar or it will be turbulent.
Oh, okay.
So in case of laminar, the velocity profile is parabolic, whereas in case of turbulent, if you are studying a turbulent flow, this velocity profile will have a logarithmic nature. It will be logarithmic nature, like it will look something like this. They will look like a straight line, and then the surface near the the fluid near the surface will have almost infinitely less velocity. So such velocities or such profiles are called as logarithmic profile, where almost every particle will have same velocity. Like you can imagine in turbulent flow, because the particles are not maintaining their layer, all the particles flowing will kind of have similar velocity, except the particles near the surface. Particles near the surface, they tend to have infinite value of velocity in negative direction.
Okay.
So, but these are something which you won't have to study in your this.
Okay.
When it comes to velocity profile, heat transfer only takes care of laminar flow. When it comes to turbulent flow, mostly things are empirical. You don't have to go through all the graphical data.
Okay.
That is something that you must know what exactly it is. Okay. So I hope you understood what is external flow, then internal flow. You understood the zones in the boundary layer, and then entrance length in a pipe.
Yes, understand.
These are some important parameters you must know for your numericals. Okay.
Okay.
So this was about the Reynolds number. The Reynolds number is a parameter or the number which signifies how the flow would be, either flowing on the surface or flowing inside the pipe.
Yeah.
Okay. Then there comes another important and signifying parameter called as Nusselt number. Have you heard this number?
Yes, I have.
Okay. Nusselt number is basically convection heat transfer to the conduction heat transfer. It is ratio of heat transfer due to convection over heat transfer due to conduction.
What is it for exactly?
Yeah, I'll explain.
Okay.
Suppose if there is a fluid, and it is in contact with the surface. Suppose there is a fluid, it is in contact with the surface. Had that fluid not been flowing, the heat transfer between the fluid and the surface would be by which phenomena?
Conduction.
Conduction, purely conduction. Okay.
Because it's steady state.
So conduction is basically how you absorb the heat or you take the heat by two phenomena, one by vibration, another by movement of the electrons.
Okay.
And you let the heat flow from one end to another.
Okay.
Then what is convection? Convection is basically when the fluid is flowing over the surface. Again, it has to carry the heat. It has to take the heat from the surface and give it to the another surface. So Nusselt number signifies that how good the fluid is if it is given the job of convection over the conduction.
Okay.
So this conduction property is of the fluid itself. what people mistake is that people think that this conduction would be for the surface which is giving the heat. But this conduction property is for the fluid itself, the one which is participating in the convection phenomenon.
Okay.
So you can say Nusselt number signifies that how good how a material would behave when it is given a job of only convection and not dependent upon its conduction parameter or properties.
Okay.
Like you can say, if suppose this fluid is not flowing, and it is asked to participate in heat transfer. So because of its temperature difference, it would take away heat and let the heat flow from one end to another. Okay. So in that case, fluid was not moving at all. So it was solely doing conduction phenomena, but it was participating in heat transfer.
Yeah.
Okay. But if the fluid starts moving, flowing, it will not transfer the heat by conduction. Now it will transfer the heat by convection.
Okay.
See, you can understand that when a fluid is participating in the form of convection, it acts like a carrier of the heat.
Yes.
But when it would be participating in the form of conduction, it will let the internal molecules to transfer heat from one part to another.
Yes.
So in that case, it will not be solely carrier of the heat. It will be like it is participating in heat transfer, but the heat might lose it anytime. Like it will flow from one of its end to another end, and it will not participate in the property of going along with the fluid.
Okay.
Right?
Yeah.
So in order to make sure that fluid is going with the fluid, heat is going with the fluid, it should have higher Nusselt number.
Okay.
Are you getting me?
Yeah.
Okay. Or in a simplest manner, you can say that if the fluid was given only to perform conduction, it would be this property, it would be this magnitude. If fluid is asked to participate in convection, it would give you this value. And if the ratio is more than 1, it is good at convection.
Okay.
Right? If the ratio is more than 1, it means it is good at convection and it will do the job.
Okay.
So that's why Nusselt number is always more than 1.
Oh, Nusselt number has to be always more than 1.
It is always more than 1. And higher the Nusselt number, it means
the better the heat transfer by convection.
Better the heat transfer by convection.
Okay.
Okay. So Nusselt number has a formula HL by K. How it has been formulated, you can understand that convection formula is HA delta T and conduction formula is KA by L delta T. And if you simplify this, delta T gets cancelled out, AA gets cancelled out, and it looks like HL by K, where L is again
characteristic length.
Yes. Okay. In this chapter, they will give you, or they will give us many equations of Nusselt number. Like equation would look like A into RE raised to something, and another parameter which we need to study now is PR raised to something. Or it can be arranged in some another combination. Like instead of multiplied to something, it will also be added to some other constant. Okay. So this formula will be given to us empirically for the range of Reynolds number.
Okay.
Depending upon the type of flow. So if the flow is laminar and it has got some range of Reynolds number, then they will give you some another equation, which is not practical to remember all the types of equation. Like there are hundreds of equations which is not easy to by heart. So they will always give us the equation depending upon the type of flow and the Reynolds number.
Okay.
Purpose of this equation would be to find the value of Nusselt number.
Okay.
Once we find the value of Nusselt number, when that Nusselt number is equated by this formula, we can find H, which is the sole purpose of this chapter, which is the main function of the chapter to find. Like this chapter is about convection. Once we find the coefficient of convection, the convection heat transfer will be done.
Okay.
Okay, so it is like, first of all, we need to know all the numbers. With those numbers, we will be finding Nusselt number. With the Nusselt number, we will find the coefficient of convection, and with the coefficient of convection, we can find the convective heat transfer.
Okay.
So that is like the subject all about. The chapter is all about. All you have to do is understand the numbers. Then using those numbers, find the Nusselt number. Then using the Nusselt number, find the coefficient of convection. And using that coefficient of convection, find the heat transfer due to convection.
Okay.
Okay. So that is the flow of the subject or chapter.
Okay.
So third number is Prandtl number. Prandtl number. Okay. Prandtl number is basically ratio of diffusivity. It is ratio of diffusivity. The diffusivity ratio is basically nu by alpha, kinematic viscosity upon thermal diffusivity, or viscous diffusivity. Viscous diffusivity upon thermal diffusivity. Okay, so viscous diffusivity was mu by rho, and thermal diffusivity was K upon rho Cp, right?
Yeah.
Then rho gets cancelled out, and the last formula which is left is mu Cp by K.
Yeah.
Mu is dynamic viscosity, Cp is specific heat, and K is thermal conductivity. This is viscosity. This is specific heat. And this is conductivity. Okay. Nusselt number, Reynolds number, Prandtl number. These are the three most important numbers you must know when it comes to forced convection, either into the pipe or over the surface.
Okay.
Okay. So there are some few more numbers which I don't know if you know them or not. The names are Stanton number and Peclet number. Have you heard it?
No.
Okay. The number is ST, that is Stanton number. Stanton number. Stanton number is, I think, Nusselt number upon REPR. ST. These are something which is not required, but just for the sake of knowing them, it is relationship with number Nusselt, RE and PR. And then fifth number is Peclet number. PECK or PEK? I don't remember. It is, I think, PEK, Peclet number. Peclet number denoted by PE. It is REPR. So what happens sometimes, you know, like in Nusselt number equation, like just now I told you that it is empirically given as some A into RE into PR, maybe raised to either raised to N or M, or both has the same power. So instead of giving us separate, or instead of giving us equation in the form of RE or PR, they sometimes might give us equation in the form of Peclet number.
Oh, okay.
Like instead of writing RE and PR, they might write a PE. Okay, so these are the only important numbers we must know for forced convection. Okay. Then there comes one more number, not one more, the two numbers. Those are important for natural convection. Okay. So when we talk about natural convection, there are 2-3 changes, like the first formula of characteristic length, the characteristic length, this changes.
Mhm.
Okay, like in this case, we had a discussion that if the fluid is flowing inside the pipe or duct, hydraulic diameter is 4A by P.
Yeah.
But if the fluid is over the surface, it is the span along which the fluid is flowing.
Mhm.
Right? It is the span along which fluid is flowing.
Yeah.
If there is a plate over which it is flowing, the D would be equal to length of the plate.
Mhm.
Right?
Yeah.
So this is for pipe and duct, and for plate and any other surface, it would be a span along which fluid is flowing. I'll just recall once we are going through numericals. Okay. So
Okay.
D for this case is span over which fluid is flowing, and D is nothing but equal to length.
Okay.
Okay. So similar way, here also we wrote characteristic length for Nusselt number. Had it been a pipe we are dealing with, if there's a case of pipe where we are calculating Nusselt number, this L will be equal to D. Okay.
Okay.
So Nusselt number is sometimes written as HL by K or sometimes written as HD by K depending upon application. If it is over the surface, it is HL by K. If it is inside the duct or pipe, it is HD by K.
HUD by K.
HD by K.
HD by K. Okay.
Instead of writing L, we
HL to D. Okay.
okay, that is characteristic length or hydraulic diameter.
Okay.
Okay. So what about the natural convection? In case of natural convection, what happens? In case of natural convection, the fluid does not flow in this manner. It always goes upward.
Upward? What do you mean?
Upward. The fluid always flows naturally upward.
Okay.
Like because of density difference, buoyancy. In
Okay.
right, in case of natural convection, if this is the length,
Mhm.
if this is the length of the plate, that won't be characteristic length. Only for the case of forced convection, you can take this as characteristic length because the span is along the flow.
Yeah.
But in case of natural convection, the fluid will go in the upward direction for convection, right?
Yeah. So you take the
No, in that case, the L becomes A by P. Area upon perimeter. In that case, area would be this area. And perimeter would be sum of all the sides.
Oh, okay.
Okay. So this is something which is signifying difference for a natural convection over the surface. So it is area upon perimeter. Okay. Area upon perimeter. Okay. But this is for horizontal surface. This is only for horizontal surface.
Okay.
If the plate is vertical, if the plate is kept vertical, in that case, the fluid would go also upward in upward direction.
Okay.
Right? And if this is the length of plate, the characteristic length for vertical surface would be equal to L itself.
Yeah. So I don't need to find area, right?
No.
Okay.
If the surface is vertical, it will again be a span over which the fluid is flowing.
Okay.
If the surface is horizontal, in that case, the characteristic length becomes area upon perimeter. Okay.
Got it.
So this is where geometrical difference comes into picture for natural convection.
Okay.
Then one important number called as Grashoff's number. Have you heard this number?
I think so, yes. I
Yeah.
can't remember.
Okay, like similar to Reynolds number,
Mhm.
there is a number called as Grashoff's number for natural convection.
Okay.
You will not see Reynolds number in this chapter. Whenever you will be dealing with natural convection, there will not be a term called as Reynolds number.
Okay.
There will always be a Grashoff's number written by GR. The functionality and the significance is kind of same. What
Okay.
Reynolds number plays for forced convection, the Grashoff number plays in natural convection.
Okay.
The Reynolds number was inertia force upon viscous force, right?
Yeah.
This is equal to inertia force into buoyancy force.
Okay.
Buoyancy force upon viscous force square. So it's like, because these are all numbers, they had to be dimensionless. So over there it was inertia force upon viscous force.
Yeah.
It is simply inertia force upon viscous force into buoyancy force upon viscous force.
Okay.
And I think you can understand why buoyancy force is considered, because in case of natural convection, the flow is solely because of its density difference. And that density difference generates the flow because of a force called as buoyancy.
Okay.
And the formula of buoyancy force is actually equal to weight of the fluid displaced, if you know.
Uh-huh.
Right? Like inertia force, we know rho AV square.
Yeah.
And then for buoyancy force, the formula is, it is weight of the fluid displaced. Weight is equal to mass into gravity. Mass is equal to density into volume. Volume is equal to area into length. Like buoyancy is weight.
Yeah.
But in thermal subject, it is not just about weight. It becomes weight into coefficient of expansion into temperature difference.
Okay.
It is weight into coefficient of expansion into temperature difference. Temperature difference between the fluid and the surface which is in contact with. And coefficient of expansion is again reciprocal of mean temperature. Okay. So formula looks like weight. Weight is equal to mass into gravity. Mass is equal to density into volume. And volume is equal to area into length.
Yes.
So the formula can be written as, see, mass is density into volume into gravity. Then this will be density into area into length into gravity. So it will be rho ALG into beta into delta T. This is buoyancy force.
Okay.
Viscous force was mu A V by L whole square. Right?
Yeah.
So let us try to simplify this formula. Area would get cancelled out. It is square over here. So it will be like they get cancelled out. Then even velocity, I think, looks getting cancelled out. Then let us try to simplify the rest. It will be like GR is equal to rho square G beta delta T. Then this L this is L square, right? So this becomes L cube. L square, right? So I should not cancel this square. V got cancelled out. Okay, so it will be like rho G beta delta T L cube upon mu square. This can be written as, if you remember new formula of nu. It was mu by rho. So it can be written over here, mu by rho. So G beta delta T L cube upon nu square. And this is the formula of Grashoff's number, where G is gravity, beta is coefficient of expansion. It is equal to reciprocal of mean temperature. And then L is equal to characteristic length.
Okay.
Characteristic length. Delta T is temperature difference. Temperature difference. Nu is kinematic viscosity. Nu is kinematic viscosity. Okay. So this is about Grashoff's number. Like the functionality of Grashoff's number is same like Reynolds number. They will always give you some range of Grashoff number for particular Nusselt number equation.
Okay.
Like I told you about Nusselt number. Nusselt number will be written in the form of RE and PR.
Yeah.
Right? This is only for forced convection. For natural convection, it will be written in the form of GR-PR. In the form of GR and PR.
Yeah. Okay.
Okay. The number called as Rayleigh number or Rayleigh number. R-A-L-E-I-G-H. Rayleigh or Rayleigh's number. It is product of GR-PR. GR-PR.
Oh,
Now,
so we just use the Rayleigh's number.
What?
We only use Rayleigh's number.
Yeah, most of the time we use Rayleigh number.
Okay.
Rayleigh's number is basically product of GR-PR, similar to Peclet's number called as RE-PR.
Okay.
See, similar to Peclet's number, which is product of RE-PR. In case of natural convection, you will always find Rayleigh's number, that is GR-PR.
Yeah. Yeah. Okay.
Sometimes you use Rayleigh's number, sometimes you use the product of GR-PR independently. Okay. Have you seen this RA number anywhere while solving numerical?
Yeah, I have.
Yes. So that is Rayleigh's. Rayleigh's number is product of GR and PR. GR is Grashoff's number and PR is Prandtl number.
Okay.
Prandtl number is again mu Cp upon K.
Okay.
Okay. So these are all the important numbers that we had to discuss and you must be knowing before we start with the concept of numericals.
Okay.
And I think we did discuss about, first of all, about the convection heat transfer, and then secondly, types of convection heat transfer.
Yeah.
What kind of applications we'll be having in forced convection? We'll be having an application where fluid would be flowing over the surface into the pipe or duct.
Okay.
Then for forced convection, we must know numbers like Reynolds number, Nusselt number, Reynolds number, Nusselt number, Prandtl number.
Yeah.
Stanton number and Peclet number are something, even if you forget, it's okay. But it is good to know them. It is sometimes like very rare you will find them to use, but you must be knowing them. So what are important relations? Nusselt number, HL by K or HCD by K. Prandtl number, mu Cp by K. Then Reynolds number, rho V D by mu or rho V L by mu.
Okay.
Rho V D by mu or rho V L by mu. Okay.
Yeah.
Then we must know some parameters like what is kinematic viscosity. We must know parameter like what is dynamic viscosity.
Okay.
And what is thermal diffusivity. This is not something you'll be using that often, but yes, thermal conductivity we have already gone through. Density, you must be knowing it. Specific heat. Specific heat is something that we normally study in thermal subjects like thermodynamics or something.
Dynamics.
Okay. Do you know Cp of some products like water, air?
I cannot recall, but is it like 1,000 or something?
No. Cp of air. Cp of air is 1.005.
Oh, okay, no, I have not
Joule per
memorized it.
kg Kelvin.
I learned it in thermodynamics, but I have to recall.
No issues. Cp of water is 4.187
Okay.
kilojoule per kg Kelvin.
Mm-hmm.
Okay, and then Cp of steam is not something that you would be using, but
Mhm.
even if it is required, then it becomes function of pressure.
Okay.
Like at every pressure, Cp changes. But for water, irrespective of any pressure, Cp is always same.
Okay.
Cp of ice is equal to 2.1 kilojoule per kg Kelvin. Okay.
Yeah.
So what else do I need to say? Like,
I just want to know like the steps, like for natural connection, what would I have to find first? What next before I can get my answer kind of thing? And also for force convection.
yeah. See, there are many things. First
Mhm.
of all, it is very important that you should be able to calculate the numbers. If the
Okay.
question is about force convection,
Mm-hmm.
then in that case, always try to calculate Reynolds number first.
Okay.
With the Reynolds number, we get to know if the flow is within the laminar range or within the turbulent range.
Okay.
Okay. Then once we know the Reynolds number, we have to calculate Prandtl number for any type of flow. Prandtl number is calculated for every kind of flow. Like
Okay.
if it is natural convection, or if it is forced convection, or if it is flow over the surface or flow within the surface, every time you have to calculate Prandtl number. Most of the time they directly give you the Prandtl numbers value.
Okay.
Like it will be 1 point something, 0.7, 0.9. Okay.
Mm-hmm.
We will talk about the significance of Prandtl number also today. Wait, because we haven't discussed about the thermal boundary layer yet. Okay.
Okay.
We will discuss that also. So thermal
Okay.
boundary layer. Okay, these are all the numbers. First of all, you need to calculate. Once you know the numbers, then the most important step would be to calculate the Nusselt number. Then after Nusselt number, mostly it goes with the calculation of coefficient of convection H.
Okay.
And then with the coefficient of convection H, you can calculate Q. Q equal to H delta T. Sometimes you also have to use that basic formula of heat transfer MCP/dT. Q
Okay.
equal to MCP/dT.
Okay.
Q equal to MCP/dT is basically heat transfer or heat lost or heat gained by the surface or the fluid.
Okay.
Let me explain how the formula differs with the heat transfer rate. Look, suppose this is one body, and if it's losing some heat,
Okay.
so its initial temperature would be, let us say, some T1, and after losing heat, the temperature would become T2.
Yeah.
So for the body itself, there was two temperature, one initial temperature, another final temperature. So for that body, how much amount of heat it has lost, you'll have to use that formula MCP/dT.
Okay.
And whatever the heat the body has lost must have been conducted and convected. Because
Yeah.
if the body is losing heat, it will be either in the form of conduction or convection. So
Yeah.
that heat lost can be equated to the heat transfer.
Okay.
But again, one very important, you can say, function comes into picture, that this value is mostly in joules or kilojoules.
Okay.
Let us say joules or kilojoules.
Mhm.
But the heat transfer rate is in joules per second.
Okay.
That is rate of heat transfer.
Yes.
So rate of heat transfer is basically heat lost every second. And what you have calculated with Q is heat total amount of lost from the body.
Correct.
So you'll have to make it function of time in order to equate them. So that is something you shouldn't be making mistake at.
Okay.
Okay, so that is about heat transfer rate and then heat capacity.
Okay.
I think, yeah, this is like the main chunk of the subject. Okay, main chunk of this unit.
Okay.
Then there is one more thing, that is thermal boundary layer, which might be asked for theoretical questions.
Uh-huh.
In numericals, it is not mostly considered, or maybe there can be some numerical solely for that distribution. So let us understand what is it. Like it is very easy. Topic of 5 minutes.
Okay.
So let us talk about thermal boundary layer. You had an hectic day. Are you okay to understand?
Yeah, I'm okay. I can't see. Can you use a different color?
Yeah, it's okay. Sorry.
Sorry.
What kind of work you do?
I'm actually a tutor.
Okay, then fine. Tutor. What do you teach?
A primary level or secondary.
Nice.
English, math, and science. Yeah.
Oh, nice.
Yeah.
Do you like the profession?
Yeah, I like it.
And if you don't mind, then why are you pursuing the degree? Like, is there some
Oh, yeah, just for myself actually. I wanted to finish it up.
maybe you can even join some engineering college after that, right?
What do you mean?
You might once you complete your graduation,
Yeah.
after your post graduation, you can get into engineering college to teach, right?
Yeah, I can do that, but I could also go into teaching in the local schools as well.
Okay, yeah, they require the graduations over there.
Yes, correct. Yeah.
Okay. Okay, let's get back to thermal boundary layer. Thermal boundary layer, we will consider two applications. One for the surface, open surface, and another for the pipe. Let us say there is one surface over which a fluid is flowing. The fluid has got temperature T infinity, and has got temperature, let us say TW, T wall. Okay. If T wall is more than T infinity, case 1, and then another case would be T wall less than T infinity. Okay, it will have a temperature TW again. Then a surface is experiencing entrance of a fluid with temperature T infinity. See, like similar to velocity boundary layer, here also you will get formation of thermal boundary layer.
Okay.
What exactly it is? That like you should if you can imagine that the moment fluid will come in contact with the surface, they will start exchanging heat.
Yeah.
More the time they will spend together, there will be more heat transfer rate.
Correct.
And with the time, the hotter body will try to bring the temperature of colder body more towards itself.
Yes.
Like you can imagine that if they get enough time to remain together, the wall, if it is hotter, and fluid which is colder, it will try to make the temperature of the fluid equal to the wall temperature.
Yeah.
Right. So it is because of this heat exchange, a membrane or an imaginary layer is formed. Like if you can see beyond this layer, the fluid is not affected by the surface. The fluid is not affected by the surface, but below this layer, because of heat exchange, the fluid will try to become like the surface. So if I draw a vertical line and say that at this point, the fluid is unaffected. So being unaffected value is negligible.
Okay.
If I go deeper, the fluid will try to become like surface. So you can say that x-axis is increasing because the fluid is trying to become like a surface. It means the temperature of fluid is increasing and it is reaching the value of wall temperature.
Okay.
The deeper if you go, the fluid will have temperature higher, and at the bottom, the fluid temperature will be equal to the wall temperature.
Temperature. Okay.
And this is the profile. This is the thermal profile or temperature profile which is generated in such type of fluid.
Okay.
This vertical distance is called as thickness of boundary layer or thickness of thermal boundary layer. If you see case 2, in this case, again, a boundary layer would be formed. On the contrary, you will see that at the uppermost point, at the thickness where the boundary layer finishes, over there, the temperature would be of fluid which will dominate. And at the bottom, it will be the temperature of the wall which will dominate.
Yeah.
Now, the wall temperature is least. So it is trying to take the heat inside.
Yeah.
So it is trying to take the heat inside. So what it will happen that at the surface, the temperature would be least. And eventually when you will go upward, you will see that the temperature of fluid is rising.
Yeah.
So you can say that over here, the surface was increasing the temperature of fluid, whereas over here, the surface is decreasing the temperature of the fluid.
Okay.
So if at the uppermost point, the temperature of fluid is highest, it will keep on decreasing. And ultimately at the bottom, the temperature would be least.
Okay.
Right? So these two graphs are basically thermal profiles. This is again parabolic in nature. Both of them are parabolic, but in opposite manner. So these are thermal boundary layers, which we must know that even these are formed while understanding the heat transfer concept.
Okay.
Look, now there are two types of layer. One layer is velocity boundary layer and another layer is thermal boundary layer, right?
Yeah.
These two boundary layers have a relation in common called as Prandtl number.
Okay.
If Prandtl number is 1, it means delta thermal and delta viscous is same.
Okay.
It means that boundary layer which is formed will have same profile of velocity and same profile of temperature if the Prandtl number is 1.
1. Okay.
Prandtl number is mu Cp by K.
Yeah.
Right? It is relation between viscous diffusivity to thermal diffusivity. Right? So
Yeah.
if the Prandtl number is less than 1, what do you say? If the Prandtl number is less than 1, what does it signify? Will the thermal boundary layer will be larger or will the velocity boundary layer will be larger?
Thermal boundary layer.
Perfect. It is the delta thermal more than delta viscous, where Prandtl number is less than 1.
Okay.
And if the Prandtl number is more than 1, in that case, delta thermal is lesser than delta viscous.
Okay.
Right?
Yeah.
Okay. So they have their own, you can say, merits. If the body is having a tendency of flowing, like I was talking about the diffusion rate. If we are talking about Prandtl number, let's understand what exactly Prandtl number signify.
Okay.
If a fluid is flowing, then there are two properties which come into picture. That is, one is flowing of the physical mass, and secondly, motion of the heat.
Yes.
So it's like if the fluid is flowing with some rate, and at the same rate, if the heat is flowing, then such fluid will lead to have a Prandtl number equal to 1.
Yeah.
But if the fluid is easily flowing,
Mhm.
but it is not taking the heat along,
Mhm.
then thermal diffusivity is lesser.
Yes.
Easily the heat was not getting into the fluid, or you can say into the bus.
Okay.
And in the opposite case, if the viscous boundary layer is not dominating, like you can say, if the fluid is more viscous,
Mhm.
if the fluid is more viscous, it's like a bus is very slow, like the hop-in hopper buses. They're very slow and easily people can ride into it. Similar way, if the fluid is very slow, easily heat can get into it.
Okay.
Easily heat can get into it.
Mhm.
And it will always make sure that heat is going along with it.
Yes.
So you are not wasting your energy in flowing the fluid. But whereas in case of, in first case, when you were wasting your energy more on flowing the fluid, there can be also a situation where fluid is flowing, but it is not taking the heat along 100%.
Okay.
So that is where Prandtl numbers signify things. And when you do all the research and understand this topic, you try to make your own conclusion that what is good for you and what is not good for you, depending upon the fluid and the surface.
Okay.
So this is all about the numbers and the unknowns and the parameters in this chapter. Then there are some parameters like bulk mean temperature. Like we need to calculate numbers for the numericals, right?
Yeah.
For the numbers, you must know all the parameters. Like if you're asked to calculate Reynolds number, in Reynolds number there is terminology called as dynamic viscosity and density, right? So you must be having these values with you before you calculate RE.
Okay.
And just now I told you that dynamic viscosity changes with temperature.
Yes.
And so changes the density. We know that density changes with temperature. If you heat the fluid, it will decrease its density, and so will it affect its the dynamic viscosity also. So in order to find the Reynolds number, you need to find all these values at a particular temperature.
Okay.
Particular temperature. Like if heat transfer is occurring between a surface and a fluid, then you need to calculate the mean value of those two temperatures. And at that mean value, these numbers or these properties are obtained from the standard table.
Okay.
Like if the temperature of the fluid is 20 and if the temperature of surface is 10, then 20 plus 10 divided by 2, 15. At 15 degrees Celsius, you will calculate density and dynamic viscosity, and then you will calculate the Reynolds number and all the other required numbers.
Okay.
Right?
Yeah.
So, fine.
What if it's given to us?
They most of the time give you all these numbers.
Or they will give it to us?
They do give you all the numbers. You must have seen the numericals, they give you all the numbers.
Okay.
Like that is where students get confused why so many data is already given. And sometimes they don't give you the number. They prefer giving you the table. Now, how your examination will be conducted. Like many examinations in our country, they are like, they don't give you all the properties. They simply give you a table. They will like just go and find your own value and do the calculations.
Oh, okay.
So that is where things get more difficult, because sometimes you don't understand at what temperature you need to get these values.
Okay.
Yeah. So that was all about it.
Okay, so can I just run through with you quickly? The steps for the forced convection is to find the Reynolds number first, and then the Prandtl number, then the Nusselt number, and then the coefficient of a H, right?
Oh yes, so correct, very good.
Okay.
But before the Reynolds number, you must have the values like density, dynamic viscosity, velocity.
Yeah, you have to have those values. If not, you have to find them.
Okay, there are some basic formulas you must be knowing. That like formula of mass flow rate.
Okay.
Mass flow rate is density into discharge. Density into discharge. Discharge is volume flow rate.
Okay.
Volume flow rate. This is mass flow rate, which is in kg per second, and density is in meter cube per kg.
Mhm.
Meter cube per kg.
But-
And this is volume flow rate. It is in meter cube per second.
Yeah.
Okay. A volume flow rate again can be simplified as area into velocity.
Mhm.
So this is simply rho AV. Okay. Density, area of cross section, and velocity.
Okay.
That this is how you'll have to calculate mass flow rate. This will be in kg per second, because you will see that formula of this Reynolds number. It has got velocity also. So in order to find that velocity, you might have to use that formula.
Okay.
Then for Prandtl number,
This will be your mass flow rate, is it?
yeah.
The
Mass-
velocity is mass flow rate.
No. This is mass flow rate. This is the velocity of flow. Simply velocity with which the fluid is flowing.
Okay.
And this is density. This is volume flow rate.
Yeah.
This is volume flow rate. Volume flow rate is, that's why the unit is meter cube per second.
Yeah.
It is also referred as discharge. In fluid mechanics, it is referred as discharge also.
Okay. So where will I use this?
You will have to use this formula to find maybe velocity.
Oh, okay.
Maybe velocity, just to make sure that if you have velocity, only after that you'll be able to find the Reynolds number.
Okay.
See, the formula has rho Vd by mu. V, velocity is there way.
Okay.
Okay. Dynamic viscosity again. The units of dynamic viscosity can be really confusing. Dynamic viscosity is a troublesome unit, you can say, that it has got a unit of Pascal second. Mu has got unit of Pascal second. Okay.
Mhm.
But many a time they don't give you Pascal second, they give you in the form of poise. So 1 Pascal second is equal to 10 poise.
Okay.
Okay. Again, Pascal second is in SI system.
Yeah.
Poise is in CGS system.
Okay.
Then Pascal is basically Newton per meter.
Okay.
Newton is kg meter per second square.
Okay.
So they can trouble you by combining all these terms. Like instead of giving you Pascal second, they can also write kg meter per second square upon meter square second. So this meter gets cancelled. This second is kg meter second. They might give you in kg meter second. So you should be able to convert these formulas.
Okay.
Okay, just don't worry. Once we will go through numerical, I'll tell you. But what you should remember is standard unit of mu is Pascal second.
Okay.
And Pascal is Newton per meter square.
Okay.
You know the Pascal, right? Pascal,
Yeah.
Newton per meter square.
Mhm.
And another important formula would be 1 Pascal second equal to 10 poise.
Okay.
That's it. 1 Pascal second equal to 10 poise.
Can.
Okay. Talking about the units, you should also know the unit of nu. Kinematic viscosity.
Okay.
Okay.
Mhm.
It is simply, you can say Pascal second upon kg per meter cube being simplified. And it is, I think, meter square per second. Meter square per second or meter square second? Meter square per second, I think. It is meter square per second.
Okay.
Kinematic viscosity. Yes, meter square per second. Have you heard the name Stokes?
No.
Okay. Similar to poise, which is CGS unit of dynamic viscosity,
Mhm.
Stokes is CGS unit of kinematic viscosity.
Okay.
Okay. They don't trouble you in this subject for Stokes and all, but they might trouble you, okay? Because this is something which is expected in second year of engineering.
Okay.
So you never know what turns around, and they might ask you in third year also.
Okay.
So yeah, I think this is it. I've already talked about units of specific heat, then density you must be knowing.
Yeah.
Yes, all the numbers are dimensionless. They don't have any unit.
Mhm.
What is the unit of h?
No idea.
Maybe you must have been saturated, but yes, I did tell you at the beginning of class, which is watt per meter square Kelvin.
Oh yeah, sorry.
It's okay. Okay, I'll just give you all this page, okay? Just go
Yeah,
through it,
I
revise it for a day or tomorrow, and then only we will go for numericals, okay?
Okay, one last one. Natural convection, right? The steps will be, the first one I have to find is,
For natural convection, you need to calculate Grashoff's number
okay,
before, and all the terminologies in the Grashoff's number, like
Okay.
G, beta, delta T upon nu square. So you must be knowing beta and delta T and nu before that.
okay,
Like Grashoff's number is the first, and then Prandtl number, and then Nusselt number, and then H.
Grashoff's number, Prandtl number, and then,
Prandtl, then Nusselt, and then H.
then what about the Rayleigh's number? I don't need to find.
Okay, Prandtl and Grashoff together is nothing but Rayleigh's number.
Oh, so instead of finding them separately, I can find Rayleigh's number.
Yes. If you have Rayleigh's number, you can directly find the Nusselt number.
Okay, yeah. Okay, got it.
Okay.
Yeah.
So, do you have any question?
No.
Okay, then I think we can finish today's lecture.
Yeah.
Revise all this content. I'll upload the video and send you the link tomorrow. And I will give you these paper like notes today itself. Go
Mhm.
through it, and maybe Friday morning we can go through numericals.
Yeah, I will compile everything and I will send it to you by Thursday night, the numericals that I can find.
Yeah, fine.
Okay, can.
Okay. See ya.
Thank you. Bye-bye.
Good night. Bye.
Night.